have to work with it. But h of t is going to be the inverse of h bar. In other words, the inverse, what is h bar? What was multiplying the e to the minus d. So that's the inverse of minus 5.555 times 10 to the minus 5 over s plus 0.111. In other words, that without the delete. And let me try to do it the same way I have it in my notes. Okay, so I'll do it the same way I have it in my notes. This is a constant factors out. So I can rewrite that as, remember, constants factor out of both L and L inverse. Both are integrals, both are linear operators, constants factor out.
Is that the first entry, just backwards? We're just going back? That's what you're saying, right?
No.
A is 0.111?
I'm just going to bring this out of the L inverse. So it's minus 5.55 times 10 to the minus 5 times the inverse of 1 over s times s plus 0.111. If that was in the dictionary, we can proceed. There are some expanded dictionaries that will have that, but no dictionary will have everything. And in our case, we're going to use the dictionary we have in the class, and that dictionary doesn't have this entry. We won't find in the dictionary, here doesn't have anything. Nothing in the dictionary we have will have 1 over s plus.
Okay.
So this doesn't exist in the dictionary. We are stuck at the point we are at this point. So to move on, we need to find what's that English. Clear? So partial fractions expansion is a technique that brings any ratio of polynomials, and will always have denominator degree greater than numerator degree. So let me make that condition. Any ratio of polynomials in which denominator degree is greater than numerator degree by a sum of terms, each one of them being in the dictionary. So this is not in the dictionary. Let me write here, need, I'm in good form. Need PFE to rewrite this so we can use dictionary. I hope you can still read it. Fill it. Mika, you can still read it?
Yeah, you said that loud.
I guess. It's hard to resist chaining letters together when we have done it our whole life. I'm really trying to get away from chaining letters together. So that brings us to the partial fractions expansion. So that's the objective. We'll always have at the end a ratio of polynomials. What do I have here? Zeroth order polynomial in the numerator, second order polynomial in the denominator. Okay? I will do the first form that we'll use for this example, and later on I will give you a modified form that is more convenient, particularly if we're going to be doing the work by computer, to make our life easier, so I'll modify it a little bit, but this is always correct. Whether our roots are real or complex, but it's not the most convenient form if I have complex conjugate of denominator roots. So I will have a range of polynomials, and let me use variable s, Claudia. Okay, so I use variable s. So I have a range of polynomials, and the denominator polynomial will have higher degree than the numerator polynomial. So without loss of generality, you can divide by the coefficient of the highest power of the denominator. So I'll write that coefficient is 1. So I'm talking about an n for the polynomial in the denominator. And let me write it. So I have a range of polynomials and strictly greater. The denominator is a polynomial, right? We can find all the roots of the denominator and factor it out. And you can rewrite that as degree denominator polynomial. How many roots does that polynomial have? N. But they may not all be distinct. I may have multiple roots, some repeated roots. So if I consider that, and I find all the roots of the denominator, and let me write I every root, so let's understand my notation here, S minus root 1 to each multiplicity. And let me make sure that I have the same symbols in the notes. So I will use the Greek letter C is the Greek pronunciation. Psi is often pronunciation in English. And have you had any class with Dr. Jones?
Yes.
What's the name that Dr. Jones gives it?
Squiggle.
Exactly. Squiggle for Dr. Jones. If you want to call it squiggle, that's fine. But don't confuse it with zeta, that's another Greek letter. Okay? That's Xi, that's zeta. They're different letters. Okay? Physics.
So what's the real pronunciation of that one?
Xi.
Squiggle. I'm just kidding.
Xi. Okay? That's the Greek pronunciation. I think the official English might be psi.
Yeah, because in biochemistry it's psi.
Psi is okay. I had a problem with the chemistry teacher when I was undergraduate who insisted on calling it mu. Not I had a problem. That's a different letter. Alright. So that's the first root, that's the multiplicity of the root. Second distinct root, it's multiplicity. And so on. And let's say I have q distinct roots. So the last one, RQ with XC Q. Okay, so here, Clear? That's the notation. So we need to be able to find the root, distinct roots, and their multiplicity. Of course, if it is already factored out, don't multiply together. I can tell you a lot of stories from exams. There was an exam in which, you know how from the disturbance we got from the disturbance S in the denominator, okay? So I gave them a transfer function that had a quadratic denominator, and the disturbance added another term, but you have quadratic times the single term. So student multiplied through, got the cubic, and then complained that I haven't taught them how to find the roots of a cubic equation. If it's already factored, don't multiply it through. All right. So here's the beauty of it. The partial fraction of this is the sum of terms, and each one of those terms is exactly what I have here in the dictionary. It's going to be 1 over s plus a to the k. So after the partial fractions expansion, I'm back in business with addition. So here is my class notation. For each root, I have as many terms as its multiplicity. So I will start with first power. I will use, in my class notes, I use this notation. If you want to use A, B, C, etc., feel free to do so. I like to have some system and also to make some things clear. So this is which root? And this is which power? So for the first root, I have C11 over, then C12. Actually, let me make sure I have the order right, the same way I have it in my notes. Uh-oh. No, no. I just want to be consistent. I mean, you can have the inverse notation. I just want to make it easy for you to be referencing the post-it notes. So that goes with the square. And how many of them we have? C1. So the last one is going to be, sorry in case I will be Hecker's rotation, C1 subscript C1.
Oh.
C1 sub C1. That's the last one. Okay? S. Oh, sorry. I forgot to do ellipsis. Yeah, all right. Okay. So these are the terms for the first root. Will continue. Second root will be C21 for the first power. The last one will be for the second root. And so on. The last root is the qth root. I will need to reclaim the board here. We will need this entry, so let me erase from the example that we have. So this will make note taking a little bit difficult because I have continuation of example in one place and theory in the other place, but I think it's really best for understanding of the class. You need to stay with it. Okay? So, very simple example. We have that h bar of s is actually minus 5.555 times 10 to the minus 5, 1 over s plus 0.111. And let's do partial fraction expansion of this. So PFE, I have 1 over s plus 0.111. What's the order of the denominator? Quadratic, right? 2. How many roots, how many distinct roots do I have? 2 of them. So I have R1 equals 0, and R2 equals minus 0.111. What's the multiplicity of the first root? 1. What's the multiplicity of the second root? 1. So the partial fractions expansion is going to be C11 over S minus 0, right? Felix?
How do you get the multiplicities?
Well, you get the multiplicity by solving the polynomial and seeing what power you're getting.
Did you get?
I will show you a very good web source. I used to use a program I had written some years ago that you have for getting the roots of a polynomial, both real and complex. But today there are much better tools than my old program. So I will go on the web and show you a nice program to give you the roots of polynomial. So, okay. For example, Felix, if I have s squared plus 2s plus 1, this should be well known. What's the roots of this one?
1 and minus 1?
No. This is the same as s plus 1 squared, right?
There you go. So that's minus 2.
Make s plus 1 squared is s squared plus 2s plus 1, right? So, what are the roots of this one?
1 and 1.
Minus 1.
Just minus 1.
Minus 1, minus 1.
Yeah.
So minus 1 twice. So the multiplicity is 2. How many times you have minus 1 as the root is the multiplicity. Okay?
Okay.
Let's move on. So, partial fraction expansion is going to be C11, first root, first power, and the other term is C21. Minus 0.11 is plus 0.1. So that's the partial fraction. So I can write this equation, but of course this is not useful unless I can find the c's. So the question is, how do we find